Hello everyone, welcome back to Computer System Design course, and this is part 2. As I said earlier, that this part contains most of the content of this lecture. So before going to the whiteboard or the presentation slide, I would like to discuss a bit summary with you guys, and let's see the list here. So first of all, I would like to discuss about the modern technology. We are going one in now, 2021, and then I will discuss about the laws that supported the development of integrated circuit. After that, I will switch to the acceleration process, the clustering system or the multi-core system, okay? And then I will introduce you a bit supercomputer. So I will discuss about the earlier Japanese supercomputer K, which is now retired, and the most fastest, now world fastest supercomputer Fugaku is, you may know, the prefecture Kobe, the Riken and the Fujitsu that made this the world fastest supercomputer right now with the Fugaku. I will discuss a bit about Fugaku. And then I will switch to the parallelization in application level. I mean how we can parallel with the application level and what are the limitations of parallelization in application layer. And the last thing that I would like to discuss, I will conclude my lecture with the hardware accelerator. The domain specific application. I will discuss about the few hardware accelerator like the FPGAs or the GPUs or other issues, and that will be conclude the lecture. So in this part, I will discuss something in the whiteboard, and as usually I have some presentation slide. So let's start with the presentation slide for detailed discussion. Okay, well, pursuit of the higher performance. As you know, the processor or memory are the composed from electronic circuit is called the transistor. Here you can see the layout of a transistor circuit, and this is the after fabrication. This is the integrated circuit inside. Is an example of the Intel Xeon Pentium processor. So there are several things we have to consider regarding the density of this transistor or the scaling of this integrated circuit. So before going to the scaling, first let's take an example of the latest technology. Here is a circuit board of iPhone 12 Pro Max. I think many of you have this device, and inside this device, if you broken down, you will get a Apple A14 CPU. So inside this chip, there are 11.8 billion transistors are integrated with a 5 nanometer technology. So if you go a little bit earlier, iPhone 11 Pro Max in 2019, that having something around 8 billion transistor. So the thing is that the technology is increasing, and at the same time we need to the scaling prediction for the earlier theorem is no more valid for the future. There are several reasons. So the first thing that is predicted by the Dennard in 1974 said that even if the transistor density doubles, in the integrated circuit runs 40% faster and the power consumption does not change. But the prediction of the power consumption is no longer valid from 24 to 26. And another theory is called the Moore's law is regarding the amount of transistor in an integrated circuit. It says that it becomes twice in every year. It also not possible from the 2010. So as Dennard scaling failed, Moore's law failed, so how the next will be? As I said, that speeding up start to fail because of the unrealistic power consumption. And also the decreasing the size of transistor were still possible, but more dense integrated circuit could not be manufactured. The way we make the device faster earlier to make the transistor size smaller is no more realistic in the future or now. As I said, the Moore's law is fall in 2010, and the now scaling theory is also fall in 2004. So now it's focusing the parallelization. So we need the acceleration by the parallelization. So what is parallelization? Is more than one processor or core are integrated together. Here's an example of Intel processor having 4 cores, AMD processor having 4 cores. As I said, the iPhone 12 Pro Max 14 has also the 6 cores. So that core work parallelly and take the advantage to run the heavy programs into the device. So here is an example, Intel Xeon Pentium 9282 having 56 of such core. So here is a typical architecture for the multi-core system. So each core having, there are separate cores, and it could be the n number of cores, and this is the network that is connected with the main memory. The actual thing is a bit complicated, but this is the pretty simple architecture, how the processor work and connected with the main memory. Now another thing is called the cluster system. In a cluster system, connecting PCs or server with a network. So many PCs and servers are that connect in a network and that work in parallel processing are the many tasks together. And here is an example of cluster architecture. So as you said that each of the CPU having their separate memory, and so this is the interconnected network by connected working each and other. So this is another way of the parallelization. So by using multiple core or using the cluster system, we can make our computing faster rather than using a single processing unit. However, one more thing I need to discuss right now is fastest computer for a very specific purpose. We call it supercomputer. In the part on, I introduced with you one of the most powerful supercomputer, Summit. Okay, let's talk about the supercomputer. As you know, in many scientific research that involve very complicated phenomena and elements and required a very complicated calculation. To solve these very specific types of calculation and phenomena, supercomputers is required. In a supercomputer, in a sense, it basically solves the problem in 3 basic steps. First, it illustrates the natural phenomena based on the theory that we have. After that, it creates the model for the natural phenomena for forecasting the outcome like the typhoons or cyclones. And finally, it finds the patterns regulatory for the large scale of the data. Here you can see that in the left side, a supercomputer K is developed in Japan, was the fastest supercomputer in the world in 2011. And the right side, you can see, is a new innovation. Is called Fugaku. Is right now the world's fastest supercomputer. And this supercomputer Fugaku is now in operation and working a lot of things, including the research in the recent pandemic, COVID-19. One professor from Kyoto University, Yasashi Okino, involved with the research with the supercomputer. He explained his experience and he said, developing a drug generally takes more than 10 years, but it could not possibly wait such a long time with a pandemic like now we are facing the novel coronavirus, because in the same time many persons are affected in the world. So a supercomputer which is extremely fast might reduce the time considerably. So The main fact of a drug invention is basically to search the essential structure of protein that cause the disease and search the chemical that perfectly fit with that protein. The computer available before that I am talking about the left side, K, having the facility is limited scale. The K can only work with a still image, and after that it eliminated and then work with this figure. However, the Fugaku has changed everything. So in Fugaku, it's possible to simulate dynamically in multiple drug candidate, and also it makes very faster result simulations. So if we want to compare these two, K and the Fugaku, K is just a dot in compare with the Fugaku. One more thing is that generally supercomputers are not designed for the ordinary purpose to use, but Fugaku places a great importance on general purpose versatility. So in that sense, it is very revolutionary. One more important thing that I would like to share with you regarding Fugaku is Fugaku wins fastest computing in 4 categories recently. However, I would like to introduce this innovation of Japan is right now is doing contributing the society within working with the corona pandemic. So now I'd like to move to the another things which is called the data center. Data center is a collection of a computer with associated component like the storage or the network for the large scale application. For the big companies or even the small companies now need to handle with a lot of data and concurrent user for their cloud service and local cloud, local office management. So that having the large scale data processing speed, but not necessarily have to the fastest like the supercomputer. This is the network and the collection of the ordinary computer, ordinary CPUs, and that is scalable. So it cost up to the $500 million, and we can see the type of data center here. For example, the IIJ data center in Matsue City. This is developed and maintained by Internet Initiative Japan International Limited. Is a company with they are basically design a data warehouse around the world. During design a data center, it is important to keep in mind to easily scalable. So based on the demand, the storage capacity and the processing capacity can be easily increasable. There are many other issues associated with the data center, but this course doesn't have to cover all of this. So let's move to the next topic, which is parallel computing. Well, let's discuss about the parallel program. If your computer system having more than one core, your program for a given task also need to be processed in parallel. So in this case, we will discuss with the example. Here you are. This is a code that typically do the sum of all the elements in a row. So this array X having 7 elements, and each element contains some value. So once you want to do the sum, it takes 7 of these steps, and finally you will get the result 26 after various steps. Now let's move to the board and discuss a bit about how the program we can solve with a parallel of 4 core processor. So here you are. For example, you have 4 processor, and this is the processor 1, 2, 3, and this is the processor number 4. I mean the core. And the data we have in our array earlier we defined is 2, 2, 5, 3, 1, 6, 4, 3. Right. So the first part, what happened? So here the term 2, 2 and then put the 5 3 here, and then 1 6, and finally 4 3. These are the x value. So in the first cycle, these 2 and 2 are added and we get the result 4. And then this 5 plus 3 is 8, 1 plus 6 is 7, and then 4 plus 3 is also 7. So the next cycle, the 8 and 4 sum together and it makes 12 here, and this 7 come here and the result is 14. This is the second step. Okay, and the final step, here we got the result 26. So in a single processor, let's count how many cycles here it could be required. Here is the 1, and then 2, 3, 4, 5, 6, the 7. So there are 7. This is the same addition here we do in a 3 cycles using the 4 processor. However, there are some limit of parallelization. So with the multiple processor, it is possible to perform multiple tasks simultaneously or in parallel. So definitely that improves the efficiency of a given task. And also parallelization can improve the performance of a single task. So a single task or a parallel task, both are possible to improve the quality. But there are some issues and facts. So let's discuss some laws and theories regarding the limit of parallelization. Okay, to realize the Amdahl's law, first let's define the speed up. So there are two things we need to consider. One is the number of processor, if it's n, and the time takes to finish the task is t. Consider n is equal 1 and it takes 1 second to finish one task. Then we can define that t1 is 1 second. However, if the number of processor is 2, then t2 time taken is 1 upon 2 is 0.5 second. And so the speed up will be 1 upon t2 is 1 upon 0.5 is twice. That makes sense. So once it takes 1 second for one processor, half second for two processor. Let's draw a graph. Here is a speed up. Sorry, here is a number of processor. And here is the speed up. So it should be if the number of processor is increased, the speed up increases linearly. So it could be lined up this. But ideally, it is not possible. So the definition is defined by the Amdahl's law. Here is the Amdahl's law. So according to the Amdahl's law, there are 3 parameters. So the serial part of a program the parallel part of a program and the number of processor. Let's denote the serial part of a program is S, parallel part of a program is P, and number of processor is N. Okay, here's P. So serial process, like you may have a array or linked list that is not possible to process in parallel. However, other data type like data structure like graph or tree, you can most of the data can be processed in concurrently. So these three parameter is defined, need to define to make how much speed up can be done in reality. Okay, so let's again consider n is equal 1. So the time taken is basically simple. The time required for the serial part and the time required for the parallel part. So once n equal 2, then the T2 is S plus P divided by 2. And if it is n, then Tn is n. Okay, so now come to the point. Let's consider to finish the task, both serial part and the parallel part, it takes 1 second. So the serial part and the parallel part takes 1 second. So the parallel part, it takes 1 minus p second. So let's write the value here, and we will get 1 minus p plus p divided by number of processor. And this is basically the time that taken by the, and depends on the serial part, the parallel part, and the number of processor. And if you want to calculate the speed up, a simple 1 upon 1 minus p plus p by n. So this is the law that Amda said. The speed up with n number of processor is dependent on the serial part of a program and the parallel part of a program, as well as the number of processor in the system. So now let's move to the slide again to show an ideal graph. This is the graph of Amda's law. So in the y-axis we have the speed up, and here the bottom line is considering the 20% serial tasks, and this line, the upper line, is indicating that the 10% serial tasks, and this is the red line is that this the idealistic or the. So we can from this graph we can show that, so even the 10% is decreased and is drastically decrease the line, and both are not follow the idealistic line. That means the performance or speed up of a given task is not only just depends upon its number of processor, but also it depends how many percent of a given task having serial and how many percent of a given task having parallel process. Okay, so the important thing is here, as long as we increase the number of processor, the speed up is not according to the result. The 100 processor having only the 10%, 10 times speed up. Because, so what does it mean? Does it mean that we don't need a system that has huge parallel resource? Exactly, that is not correct. So the Amdahl's law is for the single threaded parallel problem. But what Gustafsson said, Even we have a huge number of resources that can be utilized by increasing the unparalleled the problem in a very large scale. So when the size of a problem is increased to a large size, the ratio of unparalleled portion is decreased. So once it becomes a problem having a lot of threads, and even these threads are increased in a problem, so the speed up is rapidly, linearly increases. So I would like to conclude the limit of parallelism is like that. So as you know that with multiple processor, multiple tasks can be processed in parallel, which contributes to improve of efficiency, and also the parallelization can improve the performance of a single task, but it has a limitation. So you must consider the Advanced law and the Gustafson's law when you are applying the conceptualization of the resources. Well, now we move to the last but not least of this lecture is a hardware accelerator. I mean the domain specific architecture. So the hardware accelerator is developed to support the CPU for a specific purposes. So we can use the graphics processor unit as well as we can use the FPGA. Maybe all of you guys knows these two terms, but there are some patterns or there are some parameters like the energy efficiency or the programming effort. So if you compare these two things, so GPU is faster than the FPGA, but however in terms of power consumption, FPGA is better to GPU. So there are some aspects where which one we use. So let's start with the graphics processing unit. As I said that this is special purpose processing unit. So we have to write your different languages of programming code for this, like the CUDA, OpenCL are the used for programming language for the graphic GPU programming. And here is the architecture for taken from your textbook. Although this is the architecture of GPU is not a content of this course, however, you can have a look with this architecture for a GPU. So let's move to the board to discuss a very basic thing about the GPU. Okay, now I'm gonna discuss something about the GPU. So before going to GPU, I would like to discuss some basic thing about the GPU. So GPU, I would like to discuss what is GPU. I mean, what is basically the graphics processing unit and what the purpose and why we use the GPU and what is the difference between the CPU and the GPU. Well, in CPU, as you know, that there are several cores. They are and work in a serial for the tasks. So one task is work and then whereas in GPU there are hundreds of core are working in parallel. Well, the program we have basically it called the AppCode. In part 1 I show you the program. The program is all the computer program is transferred to a different app codes. So once the app code is executing, so there are two things here. This is CPU and this is GPU, right? So the first thing is the calculation is transferred to the CPU and executed. And here, for example, you got a chunk of code for the graphics processing or heavy extensive calculation intensive application that transferred to the GPU. So this is the way the app code is combinedly processed by the CPU and the GPU. So now why we need the GPU? Well, so I will discuss three basic things. The number one is BDI, virtual desktop infrastructure. So GPU is especially designed for a very specific purposes for the graphics unit. For example, you are a construction engineer, so you need to simulate your building in with a that needs a very high intensive CAD application. So this is why the GPU. Number two, I would like to discuss about the AI. I mean the artificial intelligence. So machine learning, deep learning. So GPU is here. So you need extensive calculation for the neural networks and simulating other things. So GPU is supporting in these regards. Finally, number three is HPC. I mean the high performance computing. Although it is not necessarily that always it have to be a GPU for the high performance computing, but there are many ways, there are many aspects that the GPU can support for this high performance computation. So this is the very basic thing about the GPU. That what we understand that GPU support for a specific purpose to support the CPU and having thousands of hundreds of code working in parallel, right? Okay, let's move to the slide again. After GPU, the next is FPGA. So I think you guys becomes tired, and to be honest, I am very close to finish my lecture here. So here is the, again, take the laser pointer. So new term, field programmable logic array. So the important thing of the FPGA is reconfigurable. I mean, you can configure your own hardware according to your basic need. So there are many applications of FPGAs, network switch, some search engine, and other financial algorithm or machine learning, deep learning, and other things. So here's the basic thing that how a FPGA works. So you have to know your one software language that you want to make your hardware. So once you write your hardware description language, you can write it down to the FPGA board. So once you make this design data, so this FPGA is ready to serve you the specific task. For example, you make a arithmetic logic unit and you embed it into the FPGA, that FPGA is ready to serve you to that. So this is internal architecture of FPGA. So there are lots of lookup tables inside this. So you can design your circuit inside the lookup table, and each lookup table are connected among each other, and there are some memory blocks and also some inbuilt circuit like the multiplier and other things that can be used for any of these lookup tables. And last but not least again is some domain specific architecture. So this is the vendor Google developed this TPU, tensor processing unit, especially designed for the deep neural network processing, and there are huge number of multipliers integrated into this board. You can see this board picture. And the next is developed by Microsoft, which is based on FPGA. This is not FPGA based, but Catapult is also designed for the deep neural network, which is based on FPGA. And in a Catapult, there are a lot of ALU are integrated in the system. Here is another is developed for another domain specific for the graphics processing. It's Google Pixel Visual Core, which is also not FPGA based, and this is a small, and this is used mostly the Google Pixel phone. You may have this phone. So these are the domain specific ones. That's a very important thing, that the end of this course, what I tried to discuss with you, and please read this step carefully. And I think this is the so far content that we discussed. In the part 1, we very basic thing like the computer, and in the part 2 we discussed the latest technologies we are helping now. Then we have some laws that are supported the integrated circuits. We discussed some the parallelization in the hardware level. Then we discussed about the supercomputer. In Japanese supercomputer K, and then the Fugaku is the world fastest supercomputer in the world right now in this moment, developed by Fujitsu and Riken. And then in parallel programs, we also limit some discussion, some limitation of Amdahl's laws and Gustafson's laws, and we discussed the hardware accelerator with both FPG and GPU. Finally, we discussed some domain-specific architecture, the Catapult by Microsoft, and PGL and the Tensor Processing Unit by the Google. So that's all for your course today, and so the topic is very researchful topic, and you can further search it on the internet, or there are some reference textbook we can study it. So make your report according to the guideline uploaded by the report, and also there is a guideline in the part 1, so you can make your report and submit it before deadline. Okay guys, thank you, hope you are enjoyed this lecture, and bye bye.